Okay, what did Dalton say happens in a chemical reaction? Point 4 of his atomic theory. If it's ionic, yes. Okay, but in general, in a reaction, yes, separated, joined, or rearranged. Okay? That's what we said happens in a reaction. In a reaction, atoms can be separated, joined, or rearranged. Okay? There's only two types of reactions that really involve separation or joining. Okay? Two types. All the others involve rearranging. Okay? And so that's what we're going to be looking at today, is what happens when atoms get rearranged or separated or joined. Right? So the first thing here, signs of that happening. Okay? What are some signs that a chemical reaction has occurred, that atoms have been separated, joined, or rearranged? Okay, change in temperature is one. Delta, by the way, means change. Okay? So if you see me draw a triangle, that's delta, the Greek letter D, and it means change in science. So if you ever see a triangle, that's what that means. Okay, temperature change. What else? Color change. Precipitate being formed. It's the state change. Yeah. It could, yeah, we could get a gas formed. Could get a precipitate form is also a state change.
If it's a liquid, it might be more viscous or less.
Okay, so we could have a change in like nature, basically. Basically what we're seeing here with all of these is that new physical properties are becoming evident. Would you agree? Okay. If a precipitate forms, it's because something that was formed is not soluble when the things we started with were. Okay? So we're seeing physical properties changing. We're seeing new physical properties. And the reason for that actually goes back to the lab you just handed in today. All substances have unique physical properties. So in a chemical reaction, we're actually forming new substances. Okay? And as a result, we're seeing their physical properties because they're different than what we started with. Okay? So easy example here could be something like this. Can you guys see that, or is that like a bad color for me to use? Is it okay? On a blue background, it's hard to see everything. Okay. You probably used this reaction to get to school today, unless you walked. If you walked, you use this one. Either one of those got you to school today. One is cellular respiration. That's the process of burning glucose, okay, to make energy. So that's glucose, that's oxygen. And what's formed as a result of burning glucose, okay, is carbon dioxide and water. Okay? If you drove here, you use this stuff. Yeah, octane, actually, the active ingredient in gasoline. Okay? If you ever pull up to the pump and you're filling up your car, there's regular, mid-grade, and premium, and they all have a different number, 87, 89, and 91. That's the number of octane, essentially, parts per million or something like that, of octane that's in your fuel. Okay? The more octane there is, the hotter it burns. Right? You don't want to put the wrong kind in. Don't think that just because premium's higher, it's better for your car. It's not. Okay? If your car says use regular, use regular. There's so many little sensors and stuff. They get too hot, you screw it up, and the check engine light will come on. Then you have to pay $100 to some clunky to plug it in and turn it off. Okay? All right, so this is octane burning in the presence of oxygen, making carbon dioxide and water. So what I start with, if I'm talking about gasoline, is a smelly liquid, okay, that reacts easily with oxygen. Okay, so I have a gas and a liquid, and when I'm done, I have two gases. Okay, I have carbon dioxide, which is a gas, and water vapor, which is a gas. Okay, so I definitely change the physical properties of my reactants, that's the things I start with, and my products, things I end with, are different, okay? Because I have different substances. So the signs of a chemical change indicate to us you've made something new. That's also what the alchemists didn't understand. I mix these two things together. I made new things. I'm magic. I can turn lead into gold, except I can't figure that one out. Okay? Again, they were trying to actually turn one element into another. Okay? But in most of their reactions, or most of their experiments, they were mixing compounds together. Okay? And atoms were being separated, joined, or rearranged, and they were making things with new physical properties, making them think. They had done something magical. Okay? When all they had done was allow the chemical properties of the substances to engage in a reaction and produce new substances. Okay? We produce new substances. Do we produce any new elements? Okay? Carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen. I don't have any new elements here. Okay? I just have the elements that I started with. All I've done is rearrange them. Okay? That rearrangement produces new substances, not new elements. Okay? Everybody with me on that? So we're going to go over the types of chemical reactions today. Understand how to identify each type. It's pretty straightforward. They all have something. They're all actually quite a bit different from each other. So it's very easy to identify whether it's a synthesis or a decomposition or a combustion reaction. They're all very different. Okay, and then we're going to learn exactly how to write them. Okay, so the first thing you should write down is one of the two examples here. Okay, because we need to talk about the parts of a chemical reaction. Okay. These are our reactants. Okay? The things that are going to react, your starting materials, are called your reactants. Okay? The things that you end with are your products, because they're produced by the reactor. See that a lot better. Okay, so all reactions have obviously reactants and products. Okay, now the two reactions we have up on the board here are both combustion reactions. Okay, that's one of the types that we're going to go over today. In combustion reactions, a hydrocarbon, that would be a compound containing carbon and hydrogen, hydrocarbon, okay, reacts with oxygen gas. Okay, it burns, essentially. Okay, and that process produces the products of all combustion reactions, carbon dioxide and water vapor. Okay, we all know that obviously burning gasoline produces carbon dioxide. This is if everything goes perfectly. Okay, does gasoline contain more than just this stuff? And it contains all kinds of additives and impurities and stuff like that. And so when we burn it, okay, some of those additives and impurities become other gases, okay, and those gases can be harmful. Combustion is never perfect. Right? We treat it like it is in Science 10, but it isn't ever perfect. Right? And so other things like sulfur dioxide and stuff like that, carbon monoxide is a product of incomplete combustion. Okay? All of those gases are also released. We just don't deal with them. Okay? It used to be a lot worse. They used to have an additive that contained lead in gasoline. Okay? That's why actually now, if you look at this regular unleaded gasoline, there hasn't been lead in gasoline in like 30 years. Okay, like it went out when I was a kid. Okay, so yeah, in Stone Age, first learning fossil fuel. Okay, but yeah, there used to be this stuff, and it had lead in it, and when you burned it, the lead went into the atmosphere. Okay, it created acid rain and all kinds of heavy metal poisoning in rivers and streams and stuff. It's terrible. Okay, but stuff burned hot, real hot, and it was made engines much more powerful when they converted it back to unleaded. Engine power went way down. Okay, so. What do you do? Okay, so let's start looking at the different, in a chemical reaction, this is the big thing. The final products are chemically different from the starting reactants. Okay, so our reactants have certain physical properties. Our final products are chemically different and thus also have different physical properties. Okay, and that we could see in that reaction we just looked at. Okay, we started out with fuel, oxygen, and we got carbon dioxide and water. Chemically different. Right, and we talked about these as well already. Okay, evidence of chemical reaction, color change, odor change usually indicates that a gas has been formed. State change changes solubility, okay, or something becomes, something condenses or whatever. Could be any kind of state change. Energy change, temperature change, hotter or colder. Okay, all evidence of a chemical reaction. All right. So our first type of chemical reaction is the simplest. Okay. Those are synthesis, or they're sometimes called formation reactions. Okay? And they're called formation reactions because they are the joining of two materials, usually two elements to form a single compound, but it can sometimes be two compounds forming a single compound, but very rarely. Okay? Most of the time it's two elements combining to form a compound. Okay? So my reactants are two elements. My product is one single compound. It's the only reaction type we deal with where we only have one product. Okay, so it's easy to identify. Okay, it's also the only reaction type where the reactants would be two elements. Okay, and all the other reactions it's different. Okay, it's the only one that starts out with two elements as the reactants. Okay, so some things you're going to see in a chemical reaction. First off, the thing that you're not going to have to do in Science 10. These letters that are in brackets, they indicate the state. Okay, so this is magnesium as a solid, reacting with oxygen as a gas. We're producing magnesium oxide, which is a solid. Okay, you're not going to have to worry about the states of matter when you write reactions. You'll be able to write them like this. Okay, you get to Chem 20, and then you'll have to know the states. That's easy. It's just a matter of looking at your solubility chart to see if something's soluble. Okay, it would either be aqueous or solid, okay, or looking at its boiling point and melting point to see whether it be a solid, a liquid, or a gas. Okay. All right, so you won't have to worry about those, but you will have to worry about these numbers. Okay, why do we have these big numbers in front of some of these, but not all of them?
Because it's an ionic compound, and there has, in this case, there has to be more of magnesium to trade with the oxygen atom.
Okay. On the right track. There have to be enough magnesiums to match up with the oxygens. Yes. In other words, I have to balance this. Remember, the law of conservation of matter says matter can't be created and it can't be destroyed. So in a chemical reaction, I need to make sure that the number of each type of atom on the reactant side is the same on the product side. If it's not, I have either created matter or destroyed matter, which means I am God because he's the only person who could do that. Okay? Since I'm not, I can't. And so my reaction has to balance. Okay? So what we're saying here is that two magnesium atoms react with one molecule of oxygen gas containing two atoms. Okay? And that makes two molecules of magnesium oxide. So, how many magnesium atoms are on this side of the reaction? Two. And there are two over here. How many oxygen atoms over here? Two. How many over here? Still two. This two applies to the whole compound. Okay? We call these coefficients. It would be like in math if you went like this, 2x. Okay, it means multiply everything behind the 2 by 2. Okay, so the whole compound is saying there are two magnesium oxide molecules. If there are two, then there's two magnesiums and there are two oxygens. Because really, what we're seeing is what we're seeing down here. Okay, similar reaction. I've got two potassium atoms. Okay, there's two blue circles. Okay, react with one molecule of bromine. Okay, so you can see there's two atoms here, they're just joined. Okay. That produces two molecules of potassium bromide. Okay, we're going to write with that. So this 2 says there's two of that. Okay. Two bromine atoms, two potassium atoms. Okay, so we put those numbers in order to make sure that we are balancing our reaction. Okay, we'll talk more about that later. All right, so the big thing about a synthesis reaction is, okay, in a synthesis reaction, two or more elements react to form a compound. Okay, either ionic or molecular, okay, to form a compound. That's a synthesis reaction. Okay, questions on synthesis? Okay. The opposite of synthesis is to take a single compound and do what with it? Break it apart. Okay, atoms can be separated, joined, or rearranged. This is the reaction that joins them. Okay, this is the reaction that separates them. Okay, when we break something down, we often refer to that as decomposition. Okay, something dies like a plant or whatever. Okay, it slowly decomposes. That is, it's slowly taken apart. Okay, so in a decomposition reaction, a compound is taken apart. Okay? In other words, it's broken down from its compound form into its two elements, or more elements, made up of more elements. All right, so that first reaction there is the electrolysis of water. Okay? Electrolysis means you essentially arc electricity through water, and it separates it into hydrogen gas and oxygen gas. Okay? It's essentially how rocket fuel is made. Okay? We separate hydrogen and oxygen. If you recall, you saw the Martian what Mark Watney was doing. Okay? When he nearly blew himself up and lost his eyebrows. Okay? He was electrolyzing water, okay, in order to make more oxygen, okay, and to get water essentially for his plants. He was taking the rocket fuel. He was actually doing the opposite. He was taking the rocket fuel, hydrogen and oxygen, putting them back together to make water. Which is what happens when you light rocket fuel. Okay? It actually makes water. It's the most environmentally friendly propulsion system you could think of. It's also, unfortunately, highly energetic, which is good for a rocket, bad for Mark Watney. Okay? He nearly blew himself up. All right, so in this reaction, we're breaking water down. So we're taking two water molecules. Okay, so if I have two water molecules, how many hydrogen atoms do I have? 4. Okay, this 2 says there are 2 water molecules. Each water molecule contains 2 hydrogens. So essentially, guys, remember, you're just multiplying, right? We're saying this is like math. This is in brackets. 2 times 2 is? Okay. How many oxygen atoms are here? Yeah, well, 1 in each, right? 2 in total. Okay, 1 in each water molecule. There's 2 water molecules. There's 2 oxygen atoms. Okay, so being able to read a reaction in terms of figuring out how much of everything there is a crucial skill in terms of being able to balance a reaction. All right, when that reaction occurs, I end up with 2 molecules of hydrogen and 1 molecule of oxygen. Are all my elements accounted for? Okay. Over here, we said we have 4 hydrogens. Do we still have 4 over here? Yes. Okay. And we have 2 oxygen atoms in the form of an oxygen molecule, but okay, we had 2 over here. All right, so it's balanced. All right. How do I know that this little 2 means it's a molecule versus if I had that, which would say 2 oxygen atoms? And the location, size and location, yeah. Okay, this says 2 separate oxygen atoms. This says 2 oxygen atoms joined. Okay, so you've got a little 2, it's joined. Okay, you've got a big 2, it means there's 2 of this. Okay? All right. Now this other one here, same idea. Okay, I'm starting out with 2 molecules of nitrogen triiodide. Okay, so how many nitrogen atoms do I have here? 2. How many iodine atoms? 6. Okay. All right. That's going to produce 1 molecule of nitrogen gas containing how many atoms? 2. Okay. And 3 molecules of iodine liquid containing how many iodine atoms? 6. Okay. So you see how it's balanced? Okay. So a decomposition reaction takes compounds and breaks them down into their elements. Okay. These reactions very often produce our molecular elements. So everybody can pull out their periodic table right now. I'm going to just quickly go over the molecular elements. Okay, so your periodic table looks like this. On your periodic table, all of the molecular elements are highlighted, okay, in different colors, so that you know what they are. Anything in yellow and hydrogen over here, okay, all come as twos. Okay, they're the molecular elements that come as twos, and also, okay, they're listed up here, polyatomic elements. Okay, so hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, okay, and chlorine. Okay, and then we also have, okay, sulfur and phosphorus, which are even more special. Okay, sulfur comes as an 8, and phosphorus as a 4. Okay, so those are your polyatomic elements. If we blow this up a little bit, easier to see that. Okay, so you can see them over here in the corner, right? S8 and P4 over there as well. All right, so those ones are special.
How does water work then if it's hydrogen and oxygen?
When it goes together as a compound, it's different. We're just saying when hydrogen's by itself,
It's a 2.
right? When oxygen's by itself, it's a 2. They're the polyatomic elements. So when they're not in a compound as an element, they come as this number. Yeah. Okay. I'll go away now. Okay. All right, so those, like I say, are highlighted on there. Okay, next reaction type. So we've gone over synthesis. Synthesis is 2 elements combining to form a single compound. Decomposition is its opposite. 1 compound breaks down into 2 elements. Now, combustion reactions. Combustion reactions are completely different from all the other reaction types. Okay, and that's because they involve burning. Okay, and we have some special rules that go along with combustion reactions that we'll have to write down here. Okay, so in a combustion reaction, we are looking at the complete combustion or burning of a substance in the presence of sufficient oxygen. Right? You guys probably all saw when you were in elementary school, okay, you light a candle, you put a glass over the candle, and eventually the candle goes out because there's no oxygen. It uses it all up. Okay, combustion requires oxygen. Okay, that's why all of our methods for putting out a fire involve essentially suffocating it. Even pouring water on it is still an attempt to suffocate it, okay, and essentially eliminate the surface's ability to contact oxygen. Okay, we soak it down with water. It can't make contact with oxygen, okay, in the atmosphere. Okay, all that fire retardant stuff. Have you ever seen that? Okay, it just makes this blanket essentially that just smothers everything in its path. You don't want to get it on you. Okay, you can be smothered as well. Okay, it's quite dangerous in that way. Fire blanket, okay, is another one. Okay, if you have like an alcohol fire or a grease fire or something like that, the worst thing you can do is throw water on it, because what it'll do is it'll splash the oil or splash the alcohol everywhere. Okay, and then it'll start new fires everywhere else. Okay, so the last thing you want to do in that situation is to have water, because it won't smother it, it'll bounce off of it because they repel. Okay, and so you want to throw a fire blanket over top to cut off the supply of oxygen. Okay, similarly, it's probably what you want to do if a person's clothes are on fire. Right, you put a blanket on them, you smother it, you take away the oxygen. Okay, as opposed to spraying them with a chemical fire extinguisher. All right, so here's a simple example of a combustion reaction. Okay, we have C3H8, which is what you use to barbecue. This is propane. Okay, propane reacting with oxygen to produce carbon dioxide and water. Okay, the products of a combustion reaction are always the same. Combustion reaction always produces carbon dioxide and water. Okay? It doesn't matter what's being burned. Okay, because we looked this morning at the octane one, which is C8. We looked at the burning of glucose, C6H12O6. Okay, all of those. But it doesn't matter what's burning. Your products are always carbon dioxide and water. Okay, always. So is that a good way to tell a combustion reaction? Yeah. Yes, it is. Okay. That's fine as long as you have the whole reaction, but there'll come a point where we'll be predicting the products of a reaction. Okay. In that case, know that all combustion reactions involve a hydrocarbon, carbon and hydrogen in a compound, reacting with oxygen gas. Okay. No other reaction starts that. Okay. This is the only reaction that has a hydrocarbon in it. Oh, sorry, you weren't here when I explained that. this is the state of matter, gas for G. You don't have to write that in science 10, you don't have to worry about it. Okay. Balancing rules, okay, for combustion reactions. We haven't talked really about balancing yet, okay, but we're going to have just a quick look at it here. Okay, so let's say I write this reaction without any of the numbers. Okay, so I'm going to go C3H8 plus. Okay, right now, is that reaction balanced? No. Okay, on this side there are 3 carbons. Over here there are how many? 1. Okay, over here there's 2 oxygens. Over here there's how many? 3. 2 here, 1 there. Okay, and obviously the hydrogens are way out of whack. There's 8 and 2. Right? I need to make this work. So with a combustion reaction, and only combustion reactions, we balance in alphabetical order. Okay, all other reactions you pick whatever you want. There's actually easy tricks for the others. Basically, start with the biggest number and work down. Okay, for this we start alphabetically. So on this side I have 3 carbons. Over here I have 1. Okay, so if I put a 3 here, okay, am I fixing that problem? No. It doesn't, right? I have 3 carbons over here, okay, and I have now 3 carbons over here. You're right, it's going to mess up the oxygens, but that's why I do them last. Okay, so I am going to come back to that. I realize that by doing that, I've just screwed up the oxygens, and that's okay. Okay? I'm balancing in alphabetical order, so H comes next. How many hydrogens here? Okay, what do I need to put in front of water in order to get 8 hydrogens? 4. Okay. All right, now I'm going to do the oxygens, because now both of my products have numbers in front of them. So now I know how many oxygens are on this side. There's 4 here, plus 6 more is 14. Okay, so I have 14 oxygens over here. What do I need to put here? 7. 7 times 2 is 14. All right, now I check everything. 3 carbons, 3 carbons. 8 hydrogens, 8 hydrogens. 4 plus 6 is 14. 7 times 2 is 14. Oxygen is balanced. Okay? All right, now, there's one other rule. Okay, so the first rule for combustion reactions, balance them in alphabetical order. Second rule, the rule of 2. Always 2 there. Didn't all get that. It's because I didn't do my Yoda voice, right? Always 2 there. That's 2. All right. And now that I've completely geeked out on you, let's get back to what I was talking about before. Okay, so let's look at, let's say this, C4H10. Okay, I want to balance this. I'm going to follow the rule I told you on the last one. I'm going to balance it in alphabetical order. Okay, how many carbons here? 4. All right, so I'm going to put 4 here. Okay, how many hydrogens? 10. Okay, so what am I going to put here? 5. Okay, so I have 5 oxygens here, plus 8 more is how many? 13. What times 2 is 13? Right, can I have 6.5 oxygen molecules? No. I can't. Okay, if I try hard enough, yeah. I get a really sharp knife. Okay, probably not. So here is what I have to do. Okay, what I have to do is I have to use the rule of 2. Anytime I have an even number of carbons, this problem will happen. Okay? Every time I have an even number of carbons, this problem will happen. So, I start with a 2. Well, I get rid of my 0.5 problem. Well, what's 1/2 times 2? 1. It's Monday, I'll let that one go. Okay, it's Monday, I'll let that one go. All right, if I double everything, I'll have twice as much of everything, and that means that that 0.5 will become a whole number. Are we okay with that? 2 halves. Oh, okay, so 2 times 4 is how many carbons? 8. Okay, 2 times 10 is how many hydrogens? 20. All right, now I have 10 oxygens in the water, and I have another 16 here, for a total of 26. What times 2 will give me 26? 13. Okay, now I have whole numbers of everything. Okay, the rule of 2 will always take care of that 0.5 problem. Okay, you ever run into that problem, apply the rule of 2. Okay, and you will every time you have a combustion reaction with an even number of carbons. Okay, so on this slide, you need to add in balancing rules, so combustion balancing. Okay, and these only apply to combustion reactions. Rule 1, okay, balance in alphabetical order. Carbon, hydrogen, anions. Second rule is the rule of 2. An even number of carbons you have, balance with a 2 you will. Okay, so if you have an even number of carbons, you start your balancing with a 2. Okay, that's the second. Okay, for all our other reaction types, we just start with the biggest number in the reaction and balance everything from there. We don't have to do it in alphabetical order, and in fact, it's a bad idea to do so. Okay, this is the only reaction type where these rules apply. All the other ones, we start with the biggest number and balance downhill from there. Don't worry, we're going to work on that. We're spending quite a bit of time on reactions, so right now this is like going right over here. Okay, do I still need that? All right, the last 2 reaction types are replacement reactions. Single replacement and double replacement. Okay? In a single replacement reaction, in both types of replacement reactions, we only have ionic compounds. Okay? Molecular compounds will never take part in replacement reactions. So these only involve ionic compounds. Okay? In a single replacement reaction, it's an ionic compound reacting with an element. Because only one thing is getting replaced. Okay? Single replacement. In a double replacement reaction, 2 ionic compounds react with each other, okay? And 2 things get replaced. But it's always ionic compounds. All right, so what we have here is our example, okay, is that I have copper as a solid, so like well, not that we have them anymore, but a penny or a piece of copper wire or something like that. And it's reacting with a solution, that's what AQ means, aqueous, okay, so it's dissolved in solution, right, of silver nitrate. This is a real reaction. If I put a piece of copper wire or a penny in a solution of silver nitrate, the following reaction will slowly occur. the copper will be replaced by the silver. And essentially, my penny, piece of copper wire, will turn from copper to silver. Okay? And my solution will slowly turn blue, because the solution will contain copper to nitrate. And all copper-containing compounds are blue. Okay? Now, this is not an immediate reaction. I don't think you can just go grab some pennies, okay, or pieces of copper wire, throw them in a solution of silver nitrate and get rich. Okay? First off, silver nitrate is hard to come by and expensive because it contains silver. Okay? But this reaction, okay, when it occurs, will produce solid silver. It'll plate out, okay, onto the wire as the copper and silver switch places. Okay? Everybody kind of with me on that? Okay, so as you can see, the metal, copper, replaced the metal that was in this compound. And that's what happens in a replacement reaction. The element that's by itself replaces whatever part of the ionic compound it's like. Okay, so metal replaces metal in this reaction. Okay, I could also have a single replacement reaction where this happens. Okay, chlorine is reacting with sodium fluoride, which is an ionic compound. Right? Who is the chlorine going to replace? Fluorine. Right. So over here, fluorine will wind up by itself, and chlorine will end up with sodium. Okay? Single replacement reaction. Whatever the element is, it replaces that part of the ionic compound. Metal would replace non-metal, metal would replace metal. Okay? How did I know to make F a 2 there?
Because there was two chlorines before, and you have to switch or replace it, so there would have to be two something else.
Partially. It's also on my periodic table that fluorine is 2. And it's by itself. It's up there in the top right corner, polyatomic elements. Okay? If fluorine's never by itself, it's 2. It's just one of those things I have to know. Okay? All right, is this reaction balanced? No. Yeah, you will. Okay, how many chlorine over here? 2. How many over there? Just 1. Okay, so what do I need to put in front of sodium chloride? A 2. Right, and this is what I'm doing. I'm just balancing with my biggest number first. I could have balanced fluorine first as well, wouldn't matter. Okay, 2 is my biggest number. So I go over here, and I put a 2 in front of sodium chloride. That fixes the chlorine. Well, what does it do to the sodium? It messes it up. Okay, so over here I only have 1 sodium atom. So what do I need to put here? Okay, does that also fix my fluorine problem? Always a good sign when you put in a number it fixes. Okay? All right. So that's how you balance everything other than a combustion reaction. Start with the biggest number and move downhill from there. Back and forth until it's done. Okay? It's actually pretty easy. All right, so a single replacement reaction, like I said, something replaces something else, but they always replace what they're like. Okay, so in this case here, you have a person by themselves and this couple dancing, okay, and a little while later, okay, the other guy is by himself, and now it's a different couple dancing. Okay, now, chemistry is old-fashioned. Okay, the guy has to replace the guy. Okay, chemistry is old-fashioned. Okay, I'm not saying that that's what has to happen in real life, because obviously it's not, but in chemistry, okay, you can never produce a compound that's 2 metals or a compound that's 2 nonmetals. Because we said, first off, 2 nonmetals would be molecular, and this only involves ionic compounds. And secondly, 2 metals never chemically bond to each other. Okay? In real life, this analogy breaks down very quickly. Okay? But in chemistry, it has to hold true. Okay? All right. Questions on the single replacement reaction? Okay, so single replacement reaction, element reacts with ionic compound, element replaces the part of the compound that it's like. Now, double replacement reactions look like they're the most complex. They're actually the easiest. Okay? In all double replacement reactions, all you do is switch the metals. Okay, when you switch the metals from one compound to the other, you create your two new ionic compounds. Okay, so in this reaction, I have calcium chloride reacting with sodium carbonate. Okay, so this is the metal, sodium's the metal, carbonate's the nonmetal. Okay, and in this compound, calcium is the metal, chlorine's the nonmetal. Okay, when that reaction occurs, they both have new partners. Okay, sodium ends up with chlorine, okay, and calcium ends up with carbonate. Okay, I've replaced and made two new compounds, double replacement. Okay, everybody all right with that? Okay, so all you do is swap the metals, and you've got your new compounds. Okay, what did this reaction produce? Aqueous means dissolved in solution. So I started out with two clear solutions. What did I produce? A precipitate. Yeah. Calcium carbonate is not soluble. It's chalk. Okay, not soluble in water. Okay. All right. So if I am balancing a double replacement reaction, okay, is this reaction balanced the way it's written? Okay, here's how we check. How many calcium here? 1. How many calcium over here? 1. Okay. How many chlorines over here? 2. How many over here? 2. How many sodium here? 2. How many carbonate? 1. How many carbonate over here? It is balanced. Okay, that's what you do to check if it's balanced. You actually have to do that. Check 1, check 2, check 3. Okay? Yeah, it's kind of cumbersome, but that's how you check. All right, let's try balancing one that's a little bit different. Let's try. Okay, so I want to start out with my biggest number when I'm balancing. Well, there's a 4 here, but there's how many sulfates? Just 1. Okay, so that's not my biggest number. My biggest number is 2. Right, so I can start with hydrogen or hydroxide, doesn't matter which. I'm just going to start here because it's the beginning of the reaction. So I've got 2 hydrogens over here. How many do I have here? 1. Okay, this hydrogen is part of this. Okay, so what do I need to put in front of this? 2. Okay, so now I have, essentially I'm saying this, right? I have 2 hydrogens and 2 hydrogens. Okay, when I do this, that gives me how many hydroxides? 2. Are there 2 over here? Okay, so that's good. How many calcium here? 1. How many over here? Just 1. How many sulfates? How many over here? Am I done? Yep. Okay, start with my biggest number, work down. All right. Questions on the double replacement? Okay, your acid-base reactions are usually double replacement. That's what this is. Okay, this is sulfuric acid reacting with calcium hydroxide, which is a base, and bases, acid-base reactions always produce. What's this stuff? I'll write it this way. Water. It's 2 hydrogens and 1 H. Okay, we just write it this way because it's easier to trace where everything came from. Okay, so water and an ionic compound, salt and water. There's anytime you have a acid-base reaction, you get salt and water. Okay, a salt, an ionic compound, and water. Okay, as your products. All right. Now, this is just talking about some of the things we've already gone over. Okay, so it's not really new. Okay, a chemical equation describes a chemical reaction, and it must be balanced, and that's what we've gone over here. Okay, that means that there must be equal amounts of substances on both sides of the reaction. So, looking at this reaction here, how many nitrogen atoms are on the reactant side here? 3. Okay, there's only one place where nitrogen atoms are located. It's right here, and there's 3 of them. Okay, how many are over here? 2 here and 1 there for a total of 3. Okay, so the nitrogens are balanced. How many oxygens on this side?
Or, no,
6 plus 1 is 7. Okay, 6 plus 1 is 7. Okay, and there's how many hydrogens here? 2. How many here? 2. Okay, so it is balanced. They can get tricky though, right? Like if stuff separates, okay, ends up in 2 different compounds, you have to account for it. Okay, it's how much oxygen is on this side and how much oxygen is on this side. It has to equal. It doesn't all have to be in one place. It's one side and the other. It's like a scale. That's why we say balancing. Trying to make sure we got the same amount on both sides. Okay. So, important sentence here. Okay, when an equation is balanced, okay, the total number of each kind of atom or ion in the reaction is equal to the total number of the same kind of atom or ion in the products. Okay, so reactants and products have to equal each other. Okay, if I'm balancing a reaction, can I change these little numbers? Has there been a reaction that we've balanced thus far where I've changed the little numbers? I can't change the little numbers. Because if I do, I change the chemical. Okay? This reaction produces this chemical. If I change one of those little numbers, I'm changing the chemical it produces. Okay? That's not something I can do. Right? All I can do is change how much of each chemical there is by putting in the coefficients, the big numbers. Okay? So I can't change the reaction. I can just change how much stuff reacts in order to make it balance. All right. So let's just do the first one. All right. So we got 3 reactions there. What I want you to do is 3 things with each one. I want you to identify the type. So compare it to the 5 types we have and write what type it is. Write it out in words. Essentially, write the names of everything involved. And balance it. Okay. I'll give you a couple minutes to do the first one, and then we'll go through it together. So let's look at this first one. And I kept recording. I guess. Okay. So first reaction here, I've got an element reacting with an element to form a single compound. What reaction type is that? It's a synthesis reaction. Okay, so that's the first thing we want to write, just synthesis. And you can abbreviate SYN. Okay. The word equation, that is writing it out in words, okay, what's this stuff? Nitrogen, okay? I don't put a prefix in front of that. That's how nitrogen appears when it's in its element form. It's not dinitrogen, it's just nitrogen, okay? And what's this stuff? Hydrogen. Okay, and they're reacting to form this compound, which is molecular, and its name would be nitrogen trihydride, right? 3 hydrogens. If we say hydroxide, that's NOH. That wouldn't happen because this is molecular. Okay, so we have nitrogen trihydride. Okay, are you seeing why it's so important to be able to do the naming? Okay, this would be, a question like this would be like a 4-mark question on a test. Okay, you get 1 mark for the reaction type. You get 1 mark for writing out the reactants, 1 mark for the products. Okay, and then you got to balance it. Right, so how many nitrogen over here? Or sorry, let's start with our biggest number. How many hydrogen here? 3. How many over here? 2. Okay. How do I balance that? What number would make them both work?
If you put 2 in front of the nitrogen trihydride.
Okay, so that gives me how many? 6. Okay, so what do I put in front of this stuff? Okay, 3. And did that 2 fix my nitrogens? Yeah, right? 2 nitrogens, 2 nitrogens. Now it's balanced. Okay, start with our biggest number, work down from there. All right, so that's what they would look like. You would get a mark for the balance. Okay, 4 marks.
Or would you write the 3 and the 2 with the words, or you just...
No, you don't, yeah. Sorry, you don't have to write the coefficients in the word equation. The word equation.
That's confused because I was like, where do I put it?
Oh, yeah, I should have said that. You don't have to write the numbers in the word equation. Okay, yeah, just in the number. Okay, get the other 2 a try here. Okay, see how those go. I'll give you a couple minutes and we'll go through those. Okay, our second reaction, we have nitrogen, which is an element, reacting with calcium chloride, which is an ionic compound, producing calcium nitride and chlorine. So what kind of reaction are we looking at? It is a single replacement reaction, element reacting with an ionic compound. Okay, so SR is how I abbreviate that usually. Okay. All right, next step, I got to write it out in words. Okay, this stuff is nitrogen. Okay, plus calcium chloride. Okay, gives us calcium nitride. And chlorine. Okay, now I need to balance. What should I start with? Yeah, calcium is the biggest number, right? Okay, there's 3 calciums over here and there's only 1 over here. So what should I put here? Okay, when I do that, it gives me how many chlorine? 3 times 2 is 6. Okay, so what do I need to put in front of this? A 3. Okay, now I need to look at my nitrogens, and they look okay because there's 2 and 2. Okay, so now it's balanced. Okay. And you'll often find with replacement reactions that you get that like 1, 3, 1, 3, 2, 3, 2, 3. It's going to be that kind of pattern most of the time. All right, how many people have done the third one? Okay, what's tricky about the third one? It's a combustion reaction. Okay, and it's got the special rule where you have to balance in alphabetical order. Will you need the rule of 2 on this one?
Yes.
You only use the rule of 2 if there's an even number of carbons and 1 is an odd. So you don't need the rule of 2 on this. If you put in the rule of 2, you'll get it to balance, but because it won't be in its lowest terms, it'll be wrong. Okay, so that's the thing you have to watch. You can't just apply the rule of 2 all the time because it'll always balance it. It does need to be in its lowest terms. Okay, let's just go over that one because it's combustion reaction a little bit different. So we already said combustion. Okay. This stuff here will be carbon tetrahydride. Carbon. Its more common name is methane. Fart gas. Okay. Plus oxygen gives water. And guys, water is the one thing you can write the common name for. Okay, so you write the common name for water, because otherwise you got people going hydrogen oxide, dihydrogen oxide, hydrogen hydroxide, like just water. Okay, just water. Plus carbon dioxide. Okay, I have to balance. I already said I'm not going to use the rule of two, but I am going to balance in alphabetical order. There's one carbon here, and there's one carbon over there. So far, so good. 4 hydrogens here and 2 here. So what needs to go in front of the water? Okay, now oxygens. I've got 2 oxygens here in the carbon dioxide, 2 oxygens here in the water for a total of 4. What needs to go in front of the oxygen on this side? 2. Now the reaction's balanced. Okay. So this is, believe it or not, this is the easier way of doing reactions. I give you the actual formula reaction, and you have to write it out in words and balance. It becomes more challenging if I give you the word reaction. How many more chances do you have to mess it up? Okay, you got all the drops and swaps and all of that, and here's the kicker on that. If you get any of those wrong, will you get the balancing right? So you got to really know how to do your formulas from names. If you don't, okay, you won't get this to work. Now, generally, you can tell if you've done that, because you won't be able to balance the reaction. If the reaction won't balance, it's usually because you screwed up a formula, okay, and not just because you're bad at balancing. It probably means you're really good at balancing, and this is an impossible reaction to balance because you put something down wrong. Okay, you put in a formula wrong. All right, try those 3. Actually, skip this one because we did that one as an example. Those 3. That's all. Okay, so on this one here, we've got, what's this stuff here? Chlorine. Okay, and it's reacting with sodium iodide. Okay, and that's going to produce iodine and sodium chloride. Okay, what kind of reaction is that? Element reacts with ionic compound. Single replacement. Okay, balance with my biggest number first, which is 2. Okay, so I've got chlorine here is a 2, but over here there's only 1. So what needs to go in front of the sodium chloride? 2. Okay, and that gives me 2 sodiums when I do that. So I got to go back over here and put 2 there. Okay, when I do that, it gives me 2 iodines, which balances over here. And now the reaction is balanced. How many people have done the next one? Okay, so what's CaCl2? Calcium chloride. Okay, and then we have Na2CO3, which is sodium carbonate. Okay, and that's going to react to form calcium carbonate and sodium chloride. All right, when I am balancing that, I should probably start with either sodium or chlorine. It doesn't really matter which one I pick. I'm going to pick chlorine because it comes up first. Okay, so there's 2 over here. How many here? Just 1. So what needs to go here? 2. Right, because I can't just put a 2 there, right? Okay, that gives me 2 sodiums. I go back over here. There's 2 sodiums already, so that's good. That's balanced. How many carbonates? 1. How many over here? 1. How many calcium? 1. How many over here? 1. Okay, so the rest of it is balanced. I just added there 2 from 1 compound. And that's going to happen sometimes. Okay? Or it's going to be even easier like the last one. I'll go down the last one. Okay, I'll give you a couple more minutes on the last one. On here. Okay, what kind of reaction do we have? Double replacement. They're all ionic compounds, right? Metal, non-metal, metal, non-metal. Okay, so they're all ionic. Okay, so that's double replacement. Sorry, as was this one. I don't think we identified that. Okay. When I'm writing out the names, I have hydrogen chloride. Okay. Potassium hydroxide. Okay. They're reacting to form water and potassium chloride. Okay, if I don't see any little numbers, everything is a what? A 1. Are those really easy to balance then? Yes, there are no little numbers. They're already balanced. Okay, everything's a 1 on both sides. So I got nothing to do here. I don't have to write any numbers. Okay. Now, when you are balancing reactions, in a reaction like this, you wouldn't write any numbers because everything is a 1. However, if this was a test and it was just a balancing question and it was a fill-in-the-blank question, what should you write in each blank? A 1, because if you don't, I don't know whether you knew they were all 1s or didn't know how to balance the reaction and left it blank. Okay, so it's fill-in-the-blank, fill in the damn blanks. Okay, put in a 1 in all of those so I know that you knew how to do it. Okay, fill in the blank, fill them in. Okay, leaving a blank means 0. Okay, so we don't want to do that. Okay, if you've had to write out the reaction yourself, obviously then it's not a fill in the blank question, and I'll know if you put no number in front, it's a 1. Okay, I know that's a weird thing, but it comes up once in a while. Okay, tomorrow you will have a quiz, and it will be on naming, a little bit of solubility stuff, and probably identifying reaction types. Not balancing, not doing anything else, just the type. Okay? I will post a practice quiz, like always, right after school today. Have a look at that tonight. All right, you should probably get your masks on before anybody gets moving. Okay? And then wipe down your desks. Easy thing. Right.